So, yes, it's not up there yet? Okay. Yes, better? Okay, good, thanks. So this electronic spectroscopy, we've gone into the atomic spectroscopy, which is electronic spectroscopy. The energy levels, I don't know if you looked and zoomed in on some of the Grotrian diagrams, but they were in the tens of thousands of wave numbers. So think about the vibrational modes. Remember, the highest frequency was like the CH stretch, and that was 3,000 wave numbers. So for the atomic orbitals and the energies of the atoms, we're talking about 20,000, 30,000 wave numbers. So huge energy difference. So in electronic spectroscopy, that's, I was trying to think this morning of an analogy that would get your mind to really grasp the difference in energy levels. So we're here in Huntsville. We have lots of pine trees. So the height of the pine tree is like the energy level differences. So an electronic energy level would be from the ground to the top of the pine tree. And the vibrational differences would be the length of the pine needles. Does that help? So yeah, when you're dealing with vibrational motion or vibrational action, that would be like the length of a pine needle on a pine tree. And then rotational levels, that would be the thickness of the bark, the bumpiness of the bark. And so you can just sort of think of the spectroscopy pine tree, brand new today, never before heard. Okay. But I was sitting there thinking, what could I use to get your mind around the various ranges of energy levels we're dealing with? So rotational levels are just bumpy, the bumpy bark, the elevation change or the thickness of the bark layer. And then the pine needles would be the vibrational change. And then the height of the tree is the electronic range. And so here we are in, this is the oxygen atom, and sure enough, that Jablonski diagram, this is the Grotrian diagram. The visible range is around, 15, 18,000, 20,000. So, this is this region right here going from 0 up to this region right there is going to be all of those visible range. If you're starting at the ground state, you see there's not a lot of energy levels with the difference from the ground state that would fall into the visible range. So, but if you had excited state oxygen, some of these up here would fit into the visible range. And so if you had, if you were able, instead of making a neon light, you could make, say, an oxygen vapor light, you would see from some of these higher transitions, you would see some lines in the visible region. We just don't ever see those because our oxygens, in our atmosphere are not excited like that. So if you zoom in on that ground state, you see some of these hyperfine splittings that are based on the spin-orbit coupling that we've been talking about and the different term symbols. Okay. And we also, in Gaussian, we can calculate the various electron configurations. I talked about this one. What is the electron configuration for the ground state oxygen? It's 1s2, 2s2. It's going to be 2p4. But where do you put those levels? And so this is showing you the way Gaussian does it is it splits the spin up electrons from the spin down electrons. It calls them alpha and beta molecular orbitals. And so these are the 3p orbitals above this line. And so you have spin up, spin up, spin up, and the px, y, and z, and then you start pairing them up. And so then you got 2 in the px. So this would be the ground state electron configuration. Then you have the spin orbit coupling. Those term symbols would give you those little hyperfine split levels. And you could come up with an electron configuration where you had them spin paired, like if we took this electron here and put it down into this orbital, then that's this excited state. And you see that's 16,000 wave numbers different. So huge difference in just putting that electron from that z orbital into the y orbital made a huge difference. So when we're moving electrons around the nucleus and changing the wave functions of those electrons, there's huge energy differences in those. So let's look at the potential energy diagram, which takes into account the vibrations. So here's that triplet P energy level state, the ground state oxygen. You bring two of those together, and we end up with this MO diagram, this molecular orbital diagram. Now, we will learn how to do this in the next section of the notes. Depending on your Gen Chem professor, some will cover a little bit of MO theory in Gen Chem 1. So maybe you had some of that, maybe you missed that. But anyway, we'll review it as if you haven't had any, because that was a while ago, and you might have forgotten some of it. Okay. And so then this, you bring two oxygen atoms together, they make molecular orbitals that go over the whole molecule. This is how the electrons are put in those orbitals, and then you make a diatomic molecule, and this is the, right here, this is the vibrational. These are the vibrational energy levels. What are these other potentials? Like this light blue one, dark blue one, yellow, red. Those are different electron configurations. And so if we, in those molecular orbitals, instead of having the spins in a triplet state, if we put it in a singlet state, we have to put both electrons in one of those orbitals. Then that's not the ground state. That's the first excited state. What if we kept them in different orbitals, but we had them still spin paired? Okay, but that would be a different one of these orbitals, or a different one of these potential energies. Now notice what's being shown. The curve itself is the potential energy from this electron cloud. So these over here, these diagrams here, are the electron cloud. And the electron cloud is what holds the molecule together. So if the molecule is going to stretch, how hard it is to stretch is based upon the electron cloud. So if you change the electron cloud, you might be able to stretch it a lot easier. You might have a different bond length. In fact, you will in most every case. These bond lengths look very similar. Let's look at the yellow one. Okay, now we've moved an electron even further away from the two nuclei in energy. And so it's going to hold on to the two atoms a lot weaker. You know, an electron is going to interact with the nucleus a lot better if it's in the lower state, like our 1s orbital. Like if the target ball, the ball in front of target, if that's a 1s orbital, that electron is in Madisonville, Spring, Livingston to Navasota. Okay, much closer to the nuclei. If I scoot that ball out to Argentina, like a 3s orbital, then it's going to have less interaction with the nuclei. And if that's in a molecule, it's going to, if you push those electrons further away, it's going to hold that molecule together with a weaker force constant. And so you have a longer vibration, you have a lower frequency in vibration, and you have a longer bond length. And so exciting that electron cloud weakens the molecule. And so you have noticed these bond lengths here. These are all very similar. If you just take this minimum and drop it down, then that's the bond length. Okay, but look at these up here. This one comes down quite a bit longer. And so the bond lengths can change on a percentage basis quite a bit. Now notice that all of these bottom potentials here, when they dissociate, they go to this triplet P oxygen, the ground state oxygen. But then this one up here, when we get up into this area, that excited state electron goes with one of the oxygen atoms, and we end up having an excited state oxygen atom. And so that's why this level here is different. They don't come to the same energy level. This one dissociates to an excited state oxygen atom. And so there's lots of different ways that these molecules can dissociate. Most of the time we have the electrons going with each of the atoms, and it's I don't like this analogy, but it's like an equitable divorce, right? They each take the same number of oxygen or electrons, and they leave, and they're in the ground state, and so on. This one, it takes one of the electrons away in an excited manner. Okay, so then it's all at higher energy. So for a diatomic, this is a potential energy curve. For larger molecules, it's a potential energy surface, but a lot of times we'll still call this a potential energy surface diagram, even though it's just a single line curve. Okay. It's easy to show for a diatomic. We're going to probably stick to, if anytime we show a potential energy diagram, it's going to be for a diatomic, but don't get in your mind that that's the only kind of potential energy surface there is. If you have a couple of geometry coordinates, like in water, say you have the two bond lengths, but if you want to hold them to be the same, and then you have the angle, you could have the angle on one axis, the average bond length on the other axis, and you could have energy. So there you could plot like a three-dimensional surface, but you'd have to restrict the bond lengths to be the same length. If you let the bond lengths vary in that particular thing, then you've got three geometry coordinates and an energy coordinate, and it's hard to plot a four-dimensional plot. So even with something as simple as water, you really can't see the potential energy surface. Okay. But it would have these kinds of features. There would be dips and valleys where the vibrations are. And so that molecule would be down in a well, and it would be oscillating around in this well. Some of those directions would be the bond stretches, and another direction would be the bond angle, and the energy would be plotted. And then, so any of these potential energy surface dips in multi dimensions, it's going to be a pit that molecule is stuck in. You excite the molecule, it comes out of the pit a little bit. You bring it all the way out of the pit, and it's falling apart. The atoms are coming off the molecule. So these pits are the places where all the vibrations happen. So let's say we get this molecule excited. It can do lots of things. And so these are all the different fates of the excited state. So lights come in, it's knocked an electron out further away from the nucleus. It's an excited situation. And it can move from one potential energy surface to another. So every different electron cloud that you could have with the spin ups or spin downs, those would give you a different surface. Just like we saw here. Every one of these potential energy surfaces is a different electron cloud. So if we excite an electron into, say, this level, now we're on this surface here, we might be able to move from this surface over to another surface, and then over to another surface, and then to another one. And so we could work our way back down to the ground state. And if those surfaces have the same multiplicity, meaning the same net spin, same character of all spins up or spin paired, then that's called internal conversion. If the multiplicity is different in those potential energy surfaces, then it's called intersystem crossing. So this is the vocabulary of discussing this non-radiative relaxation, where the molecule is moving from one potential energy surface to another. Don't really have any analogies for this, except maybe you have, it's easier to think about it in those two-dimensional potential energy surface diagrams, right? You see this, and we'll see some pictures of these things. Okay. And then dissociation. So if you have a really excited molecule, it can move to a potential energy surface that's not bound. So it doesn't have a dip in it. It just goes downhill to an atom coming off the molecule. And so whenever you break a bond or whatever, you have dissociation. And then predissociation. This is an internal conversion that goes to an unbound potential energy surface. We'll see pictures of all four of these. So we'll just describe it with pictures in a little bit. So do you understand the difference between dissociation and predissociation? So dissociation, you're jumping up with an electronic excitation. So light comes in, sends the electron cloud to a particular potential energy surface, where now that electron cloud will not hold on to an atom. If it's diatomic, it'll break just the single bond. But if it's a if the polyatomic molecule, maybe that electron cloud just breaks the molecule in half. Say you've put enough electrons into the antibonding orbitals that now you have the same number of antibonding electrons as bonding electrons, and you've just weakened this bond, and it vibrates and goes out. So that would be with like a photon of light coming in, hitting that unbound potential energy surface, and you're breaking a bond. Predissociation is you go up to a bound state, so the molecule could stay together, and then it hops onto a different potential energy surface that breaks a bond. Let's talk about emission of light. That's another couple of fates of excited states. You could emit light in a manner called fluorescence or phosphorescence. So these are two more fates of excited states. And so singlet to singlet emission would be fluorescence. It would also be also triplet to triplet. The key just being that it's the same at the top and the bottom. So when it emits light, if they have the same multiplicity, then it's going to be fluorescence. But if you're going from one to another, if you're going from triplet to singlet or singlet to triplet, then you would have phosphorescence. And look at this lifetime. So what do we mean by lifetime? So if we're looking at a substance that fluoresces versus a substance that phosphoresces, if you have the light on, you're pumping the molecules up to the excited states, and then you turn the light off and turn on your detector. And so then the detector's looking at that substance, and you see that it's emitting light. The light turned off, and then your substance is emitting light. But that light coming out of your substance decays away pretty quickly. So that's fluorescence. You've seen fluorescent things, fluorescent Post-it notes, fluorescent paint, fluorescent shirts, and so on. And if you turn the light out, you probably don't notice it, but it'll emit light for just a few milliseconds or microseconds after you turn the light out, okay, which is pretty cool. We could probably set up an experiment here in the department that would measure that lifetime. Okay, you just fit it to an exponential curve, find the T1/2, and so on. Okay, but phosphorescence, there you've got something in the light, and you turn the light off, and it glows in the dark. And so this is all of our glow-in-the-dark stuff that we're about to see for Halloween. Using a highly technical term stuff. Okay. And so that's really cool. I like phosphorescence. And so you charge it up, you're exciting the molecule up into the excited states, and then you turn the light off, and it has a really long lifetime. It can be seconds to minutes before it decays away. Okay. And so this is an allowed transition. The fluorescence is an allowed transition. So remember all of our symmetry. If it's an allowed transition, then the two wave functions overlap, and the light is part of it, and so you have this integral that is a non-zero transition moment integral. But in phosphorescence, it's forbidden. So it can't emit light, but it does. Some sort of fluctuation happens, some kind of tiny little interaction breaks the symmetry, and then it's allowed. So it's just a statistical thing. It kind of leaks out. So in general, it's trapped in that excited state. But again, if maybe a collision comes along, changes the symmetry, and then it's allowed because it's reduced the symmetry. So if you have a really symmetric molecule like we had in benzene, but then some molecule bangs it and now it's no longer a D6H molecule just for a split second, then that transition's allowed, and then it'll give off its light. So let's go through those different fates of excited states based upon the potential energy surfaces. How many people have seen the game Pachinko? Pachinko? It's the loudest game you've ever seen because of these little steel balls. And it's like a pinball. It's really vertical. You hit this lever, and it shoots a steel ball up into the top, and then it rattles around through these little pins. and there's little cups at different levels, and they land in the cup, and it gives you like a bonus set of balls, like a jackpot. You know, it might be 50 more or 100 more or 1,000 more, you know, if you hit it big. And so that's the way I think of this process. So light comes in, a photon of light comes in, this is absorbed by the molecule, and it's shot up here to this excited potential energy surface. And then that molecule bounces around through its energy levels. Why and how does it do that? Well, it's moving, you know, in that new energy level. It's vibrating. It's also rotating. It's distributing that energy among its other degrees of freedom. This electron cloud has changed. And so now everything the molecule feels has changed. And so it's going to distribute that energy in its vibrational modes, in its rotational modes. And those are not visible transitions. They are microwave and infrared transitions. But because we're dealing in the visible range, we call it non-radiative. So we don't see that light. It's in the infrared or it's in the microwave region. So don't get caught up in the technicalities to say, yeah, but it is it's radiation that's coming out of it. It's in the infrared, though. When we're talking about a non-radiative relaxation in this, we're talking about it's not visible. It's non-visible radiative. So we call it non-radiative. And infrared is very similar to heat, so we could just say, yeah, it just heated the object up. So it's not in a visible range, so we call it non-radiative. And then we get down here to the bottom, and it reaches the ground state in the excited electronic state. So we're at V equals 0 up here. And it's stuck. It can't go down any further. And it'll sit there until who knows what, and it jumps down and spits out a photon of light. So this is then fluorescence. So it's coming out. So that's a radiation decay, a radiative decay. So this happens incredibly fast. Remember earlier, look how fast it happens. We don't really have a time scale on here, but this may be 1 millisecond or even less, 1 microsecond. So it's out of there. And so then that is given off as heat. Here's an intersystem crossing. So we have absorption, light comes in, and if you really zoom in on the notes, it hits this. We're at a singlet state here, and it hits the singlet potential energy surface here. So right above the ground state, like the most probable location for the wave function, is this vibrational level on this singlet state up here. And so it goes a singlet to singlet absorption. It's got to be an allowed transition for absorption, so it can't go singlet to triplet for absorption. It can go triplet to singlet in emission, because that's phosphorescence. But it hits that singlet state. It starts to go down through the singlet state transitions. And right here, we have two vibrational levels that are very similar in energy. Notice they have a different width, okay, but they have the same sort of vertical energy. And so here we've got, let's just take 2 electrons. So in the ground state, we have a spin up and a spin down electron. Light hits one of these and takes it to a higher level. And so now the molecule has a weaker electron cloud, and it starts vibrating in that cloud and changing its vibrational quantum numbers. And it gets to a particular vibration that matches the vibration on this state, where this spin flips, and now we have a triplet. We have 2 unpaired electrons. And there's no energy penalty for that. When the vibrational levels are the same, you can change the electron cloud, and there's no energetic penalty. You're just now on a different surface, but now you're on a triplet surface. And then you can start rattling down that triplet surface. Notice the singlet surface ends here with V equals 0. But the triplet surface, it goes down in a little bit lower energy. So every one of these potential energy surfaces has a ground vibrational state. So anyway, at that vibrational state where they match, you have this inner system crossing. I don't know, the little symbol they used in the book is this kind of a circle. It's just to show something happened right there. And now it's on this surface, and it rolls downhill till it gets to the V equals 0 state in the triplet electronic state. And there it's stuck because the transition dipole moment between this wave function, psi, I don't really want it, what do you want to call it? Let's put a triplet up here, and light, and the singlet triplet is equal to 0. So when I say it's forbidden, if you did that transition dipole moment integral, you would get 0. So it can't emit light, but it does. Something comes along and changes the symmetry, either of the upper state or the lower state, now that for a split second, that transition is allowed, and some of the molecules spit out some light. The rest of them are stuck. Then something happens to some more of them. Symmetry changes, they're allowed, it leaks out, spits out some light, but there's a lot that still haven't experienced that. So statistically, it takes a long time for them to spit out that light. And that's why the phosphorescence lifetime is so much longer. Let's look at the arrows. Notice the absorption arrows are always the longest arrows. What does that mean for the energy differences? Remember, a transition is a difference between energy levels. So if you have a long arrow means a big delta E. Make sense? Okay. Big delta E means, well, it's equal to h nu. So big frequency. And what's nu? It's C over lambda, HC over lambda. So small wavelength. So that's what I was trying to get to. As the arrows get longer, the delta E gets bigger, the frequency gets higher, and the wavelength gets smaller. So this is going to be the short wavelength. And this is going to be long wavelength. And I want to really emphasize that. Same thing over here for phosphorescence. Notice how much smaller that phosphorescent arrow is. So that's going to be a longer wavelength than the absorption. So you have the absorption spectrum, and then to the red shift, or the red side of the spectrum, are all of these emission wavelengths. Okay, let's look at dissociation versus predissociation. We see this in the iodine spectrum that we'll study in about 3 weeks. So we see from the ground state, you see all of these arrows coming up, and they hit, this is sort of the spectrum that you would see on its side. You would see a peak associated with that vibrational difference, a peak there, a peak there. So you see each one of those peaks is going to give you a peak in the spectrum. And they get closer and closer together because of what? What's the term that we use to describe these vibrational levels not being equally spaced? So think back. Anharmonicity. So because of anharmonicity, the energy levels get closer and closer together until essentially they seem to merge, like the difference between the energy levels tends to go to 0. And then you're above this point and you have a continuum of absorption. So continuum of absorption, all that means is that, notice you don't have discrete lines anymore. It's just any wavelength could be absorbed. Okay. Why is that? Well, because it's now kind of what we would call a classical situation. Think of this think of this molecule as a particle, and you're exciting it, and you're putting it up here on this potential energy surface as if it were a ball on a hill. What's going to happen if I raise the ball up this high on that hill? It's going to roll downhill, go through all of this vibrational manifold, and then leave. You ever play the carnival game where you're supposed to roll the bowling ball down the hill, get it over the middle hill, and get it stuck in that well? Anybody see that one? It's a great game. It's really hard. That's one of the few that I've been trapped by. It's like, just move it a few, millimeters higher or lower and try to get it trapped in that well. It's a very difficult game to do. But anyway, that's what it makes me think of. So if you put that ball, you can put that ball anywhere. Essentially, quantization is gone at this point. You can put that ball anywhere on this hill, and that's why any wavelength can be absorbed. So when you lose that quantization, those discrete transitions, now you're dissociating the molecule. So if this is a way like where that spacing goes to zero, that tells you then the something about this energy difference here and this energy difference here. So that's how we calculate a lot of our bond energies, is we'll look to see how much light it takes to break the bond, to reach that dissociation limit. And then if we know what this difference is, because maybe this went to, two atoms, A plus B, and this went to A plus B star. If we look at the Grotrian diagrams for the energy difference between B and B star, that's this energy difference. And so then if we convert this absorption arrow and we subtract out the atomic energy difference, then we get the dissociation energy in the ground state. So this is how we find our bond energies. There's one way to find them. Okay. And you'll do that in the iodine lab. Now, sometimes you have quantization here. So you have quantized energy levels, and then you're missing an energy level. There's no peak there. And then you get your energy levels back. And so that's evidence of this thing called predissociation. And so you see this nice pattern of vibrational differences. You see it reappear here. In this region where it's missing, you've found an intersection in potential energy surfaces. And so then for a small space there's a continuum of unbound states just in this nice little region that's grayed out. Okay. So in that region there's a continuum of unbound states. And so in the middle of the quantized vibrational transitions, there's a little continuum region where you're dissociating the molecule. So that's what predissociation is. And so those are just some missing vibronic transitions. It's the first time I've used that word in this lecture. So that's vibrational and electronic added together. So you have these electronic transitions that are going from vibrational state to vibrational state. So it's a combination of both vibrational and electronic changes. So we're going to say from V, we'll call it double prime because it's in the lower state, equals 0. Up here, let's say this is 0, 1, 2, 3, 4. So this is V prime equals 4. And this might be the electronic state X, and this might be the electronic state A. And so we would say this is an electronic transition from the X to the A state, and the vibrational transition from the 0 to the 4th vibrational state. And then there are also rotational lines in there, but they're so close together we don't resolve them typically. Let's focus again on the different wavelengths. Remember I said the absorption arrows are the longest arrows. And so those are going to be the shortest wavelengths. Sometimes they overlap, and if they overlap, it's the 0-0 transition. So where would the 0-0 transition be? I'll draw it right here. So this is an arrow going from V equals 0, V double prime equals 0 to V prime equals 0. And then this would be the arrow that comes down. So one of these is an absorption arrow, the one with the arrow going up, and the one with the arrow going down is an emission arrow, and that's shown right here. So the black curve that's shown here is the absorption, 0 to 0, and then this blue one here is the emission, 0 to 0. Let's look at this one. This was going to be V double prime equals 0 to V prime equals 1. So it's a longer arrow. Since it's a longer arrow, it's going to be a shorter wavelength. So that's this one shown right here, 0 to 1. And then this one is going to be to the second level up there, the third. So we'll draw a line down here. 3, this one, 4. So this is a way to assign this spectrum. If I just draw a line down to each of the peaks, I can draw a line across here, and I could say these are all from V double prime equals 0 to V prime equals 5, 4, 3, 2, 1. You see how it's labeled? So a lot of times these spectra in the visible region are labeled like this. If you can resolve their vibrational transitions, these peaks, so you have a big electronic peak, and then inside the electronic peak you have some vibrational transitions, and you can label those vibrational transitions. We could label the same over here. So this would be V prime equals 0. So we've done radiationless decay, and now we're here at V prime equals 0. And it's dropping down to the various levels in the V double prime region. And so then this might be, well, this one is 0 here. I'll put 0. If I go from V prime equals 0 down to V double prime equals 1, you see how that's a shorter arrow? The 0 to 0 transition was a certain wavelength. If I go from 0 down to 1, it's a shorter arrow, so it's going to be a longer wavelength than the 0-0 transition. And then if I go down to 2, that's going to be a shorter arrow, and 3, that's going to be a shorter arrow. So these all march out to the long wavelength side. So then this one would be 3, this one would be 4, this one would be 5. So V double prime is equal to these numbers. So they're all starting from V prime equals 0, going down to 0, 1, 2, 3, 4, 5. So I'm just trying to get you used to looking at the way these are assigned with this little manifold line and the various lines that go down to the transitions. Anything I can clarify on this? Okay, let's get to the Jablonski diagram, because that's the main point for today. The intensities of these peaks are based upon the Franck-Condon Principle, which is essentially what we've been teaching this whole time. It's the overlap of the wave functions. The Franck-Condon Principle doesn't use light in the middle. It's just saying if the wave functions overlap more, that'll be a more intense peak. If they overlap less, it'll be a weaker peak. And so it's the transition moment integral, but without the middle piece. And so this gets really, like I said, really complicated once you get above a diatomic. And so on the left is a diatomic. And then the Jablonski diagram here is for all types of molecules. You could use it for a diatomic, but it's mostly for bigger complex molecules. You have the potential energy surfaces labeled as S0, T1, T2. So this S0 would be the ground state. So this would be this one, S0. This would be T1, and this would be S1. The x-axis is you know, it's just it's not really an axis. It's just categorizing things by these different potential energy surfaces. So it's really just categories. Kind of like the Grotrian diagrams. The x-axis really wasn't numerical. It was just categories of different electron configurations. Same thing here, but for a molecule. And then we can show all of these different transitions. We can go from a singlet to singlet, that's fluorescence. We can go from a triplet to a singlet, that's phosphorescence. We could go from a singlet to a singlet, that's internal conversion. And if we go from a singlet to a triplet, that changes the multiplicity, so that's intersystem crossing. So we have all of these things. So let's kind of just show this all together. If this absorption here, that vibrational manifold would be given here. Notice these lines are not accurate. These are just lines drawn to show vibration and rotational levels. This orange one, the upper singlet one, would be drawn there. The triplet would be drawn there. And so, again, the only thing accurate in this Jablonski diagram are these minimal energy levels. So this is an accurate mark, and this is an accurate mark. Okay, does that make sense? That's the only accuracy. So the minimum of those potential energy surfaces is accurately represented. So the molecules are pumped up, say singlet 0 to singlet 1, and then the pachinko game starts. The ball starts bouncing through. It could give off infrared heat as it relaxes. And so this is just walking you through non-radiative relaxation is that distribution of the energy and its vibrations and rotations. Infrared emission, collisional cooling, and so on. None of that stuff is in the visible region, so we call it non-radiative. They could have intersystem crossing over to a triplet state. Changes in multiplicity, so it's intersystem crossing. We also have non-radiative relaxation. We could do that again and make it all the way to the bottom. Or we could have done intersystem or internal conversion over to the singlet 0 state and then just worked our way down through the vibration and rotational levels all the way to the ground state. And so this molecule would not necessarily emit light. It would receive a photon and then be able to make it all the way down. But if it does get stuck in those ground states, it could give off fluorescence or phosphorescence. So these are visible transitions. So we call them radiative transitions. And that would be a visible emission. Fluorescence would be visible with no change in multiplicity. And phosphorescence is visible with a multiplicity change. Now, what absorbs these lights? It's always the electron cloud. We're doing electron spectroscopy. And there are certain functional groups, which you probably learned in organic, that absorb light, right? It's the non-bonding electrons. You could have an N to pi star transition. You could have a pi to pi star transition. So we categorize these things. We will learn a lot more about these different categories in the next section. Because some of these things can give color to the molecule, they're called chromophores. So chromo, again, meaning color. So these are the things in the molecule that can cause it to be a colored substance. In the past, they tried to use these to kind of understand what the functional group was, but these peaks are so broad. So you've got a spectrum here, and you've got this peak. This is what it looks like. Okay, lambda max is here. But look at the plus minus on that thing. You know, it might be plus or minus 40 or 50 nanometers. And so it's not really helpful. You know, you can't really tell that, much difference between, say, benzene and a nitroso compound or this carbon nitrogen double bond. And so really intensity might be a little more useful because the intensities are so much so drastically different depending upon the shape and size of the molecule. But pretty much structural information from UV vis is not that easy to get. I did show, this was some work for a paper that I did on color. This week's the color lab, where you learn about transforming visible spectra into standard RGB values. And so the stuff that you learn in this week's lab, I implemented in this spreadsheet that can take a Gaussian calculation. So we did a Gaussian calculation on this molecule here. Did the UV vis simulation, which is a technique called Zendo. And it gave me these transition wavelengths and the intensities of those. And so then I take this spectrum and I use the Gaussian simulation spreadsheet that you used in the last lab, or maybe a couple of labs ago, with the chlorobenzene, benzene, and simulated the spectrum based upon this transition wavelength and this intensity. And so then that gives me this spectrum right here down at the bottom. It's not very strong because look at the intensities, 0.01 and 0.19. Pretty weak. But think about that. That's the absorption of a single molecule. Not going to be very colored. If I just have a single molecule that's absorbing a few wavelengths of light, it's not going to be a very strong absorber. And so then I just multiplied that absorption spectrum by this concentration factor, because absorbance is proportional to concentration. So if I double the number of molecules, I doubled the absorption. If I run it up to 1,000 molecules, I've increased the absorption by 1,000. And these are all of the spectra that I get from these concentration factors. Now, what you'll learn this week is that the standard method for converting spectra into RGB values uses transmission. So I converted all of these absorption spectra into transmittance curves. And now you can see how as you increase the density of the molecules, the absorption of those molecules, you start to cut out certain regions of light. And so this molecule is giving, no matter how strong or how many molecules I always have red light coming through. I take these transmission curves and turn them into RGB values using the very stuff that you're learning in this lab. And so from the transmission values, I get these RGB values. And these are the colors of the different concentrations. So as I increase the concentration of the molecule, it starts out a little bit yellow, and then it goes to kind of a pink color and then a deep red. And so this molecule, I'm predicting to be red. Okay, it turns out to be accurate, so that's pretty cool. Here, if I take one of those aldehyde groups off, it's more purple, because I have red over here, and I've got a little bit of blue. So you mix red and blue, you get purple. We kind of see that here. I take both of those off. This is a molecule called azulene. Okay, azul is blue, and so sure enough, the molecule is blue. And then if I put fluorines on it, those have a different character than the aldehydes, and so they shift the peak. Notice what happens to the absorption peak. It's red shifted. Because it's red shifted, I get a little bit more blue light in. And so this is just a nice little show and tell of what you can do with the math behind simulating the spectrum, which you learned 2 labs ago, and then the RGB values, which you're learning this week, and converting transmission spectra into RGB values. So hopefully you enjoy this week's lab. Bring a colored object to lab, like, I don't know, find something that you like. It could be a picture, it could be a ball cap, it could be anything. Your notebook, and you'll get some color spectra.